So let's have a look at the double slit pattern now and try and work out how this gets together. So you've got a monochromatic light source there of one colour, okay? As it comes through this slit, which is very important, that's going to cause diffraction to occur, and that allows us to behave like a point source which sends the waves to those two slits like this. Now that ensures that the waves coming out of here are matching, which means the sources are now coherent. And if you can continue that on, those waves will continue to spread over that way, and these will as well, and you're going to get an overlapping of the waves through here, through this region, okay? So that will cause interference to occur at this screen here that you place there, a distance away. And where the two have travelled like this to get to here, they've travelled equal distances, so the waves arriving there, and you can draw them as transverse waves, the waves arriving there are going to give you a large wave. So in terms of a pattern then, you're going to get a bright band through here with the centre of it at the maximum. That's the sort of picture you're going to get there. And we've already talked about this idea that when you go to different distances then, we're going to have a path difference there like this, which might be equal to a half a wavelength. And so they're going to arrive out of phase, and this will be a dark band. So you get an alternating pattern of bright and dark bands. So the sort of questions you might be asked in the exam is to describe the pattern, in which case you say it's an alternating pattern of bright and dark bands of equal width or equal separation. Okay? If you're asked to draw the pattern, you could draw them as alternating red and dark lines through there. Okay? So that would be the sketch the pattern. If you're asked to sketch the graph, that's slightly different there, because the graph for that, if we look at it, you sort of go like this, the matching graph of this in both directions would kind of go like that, with intensity that way, and this is the position X against the screen, and you'll be drawing this as a maximum, and it goes down to a minimum, then up to a maximum, down to a minimum, and so on in both directions. But again, with an equal sort of separation there. So that's the graph sort of thing that you would draw then, and that's a result of constructive and destructive interference. If you're asked to explain why you get a pattern there, there's a combination of things here. The diffraction here allows this to be coherent sources, and the diffraction here allows the waves to overlap on the screen, and then it's just a question of the fact that they travel different distances from each point here to the point on the screen, and whether they arrive in phase or out of phase determines if you're going to get constructive interference or destructive interference. So I've got some notes on that as well. So the key things to bear in mind here are in the notes. The double slits are narrow, and that causes the light waves to diffract as they pass through them, and you're getting coherent sources because they come from the initial single slit. That allows them to overlap on the screen, which is really important to get interference. Now, because they travel different distances to each point, you're going to get constructive interference when they arrive in phase and destructive when they're out of phase, and that gives you that pattern. Now the pattern can be described, and I apologise for the green writing there, is that alternating bright and dark bands or fringes of equal fringe separation. Okay. Now you get destructive there when they're out of phase. It should be pointed out that they get less intense as you move away from the centre, and the reason for that is that if you look at it, you've got single slit diffraction occurring in here where the light diffracts to different points. And you've got to remember the diffraction, most of the light goes towards the middle here, and there's a minimum there, and then it goes off to the side. So the interference pattern needs to sit inside this here when it happens. So your interference pattern won't be, like I've just drawn before, perfectly the same height like this. Okay? It actually sits in here where they're really dropping slightly in intensity because less light is diffracted to the side there compared to straight ahead. And you might actually lose some maxima there off the side if you go far enough out. The interferometer we use generally focus on this section here, so you would just see light beams like that getting slightly weaker to the sides, and you don't see this effect on the end here. So the diffraction sort of determines how much light goes to different positions, but you've got interference because of the two slits occurring within that. So in reality, this should go more like that. So you should actually be drawing it, when you draw typical patterns like that, you might start off tall and you might sort of just go slowly going away to the side if you're drawing it more accurately there. Because of the diffraction there, more light goes to the centre and then slightly to the sides there. Okay. Now if you try to do the same thing with white light source here, place this to the white light one. White is made of a mixture of colours from red through to violet. and those colours have different wavelengths. You've got red with very long wavelength compared to violet, and it gets smaller and smaller as you get down to violet and blue end, and these are narrow wavelengths. So you're going to have a whole range of these wavelengths coming through here, but the thing is that they will actually be diffracted to those 2 points here, so they'll still be coherent for each individual colour. So if you did one colour at a time, you would get the pattern occurring on the screen simultaneously and stable, but the unfortunate thing is you'd have red sitting on top of, or rather red, wide red one maybe, would be there, and on top of that, you would have narrow patterns from each of the colours all sitting on top of each other. So you might find that all the colours are a maximum here and you get white light and you get a whole range of different colour mixes going to the side here. So it still does work, but it'd be virtually impossible to use it for any measurements and stuff like that. So that's why we don't tend to use white light these days in this last 20 years. The worst thing you could do is to try and remove the single slit. So if you got rid of the single slit here and you use the monochromatic source like a sodium lamp here, which is fairly close to monochromatic, you would find that even though the colour's correct and you're getting the same wavelength coming out here like that, you've got multiple sources in there. Because if you expand that, it's actually a gas there. So sodium lamp's actually a gas made up of millions and millions of atoms in there, all at the same frequency pretty much, but not at the same phase. So some from here might be going in this phase, some here might be actually coming like that in another phase, and the waves going to there will travel different distances and have different phases, and they will not match the ones necessarily going to here from other points on the gas. And so these two sources here will not be matching, okay? So they'll be incoherent because they will not maintain a constant phase relationship. So removing that single slit will stop it working, and you can try that in the practical. Okay, thank you.